All right, guys, how's everyone doing? Hope you all had a good weekend. Hope the test went well. Yeah, haven't finished grading those tests yet, but you will be getting those back soon. All right, probably today or tomorrow. I'll be done grading those, just finishing up. So for today, we're going to be looking at the volume of prisms and something called Cavalieri's principle. So we talked about prisms last lesson, and let's just read our definition of a prism again. And that was of a polyhedron of which two faces are congruent polygons in parallel planes, right? And those congruent bases, they're going to be connected by parallel lines. So let's take a look at our first prism here. This is a rectangular prism. It's a prism made up of rectangles. The bases are rectangles. So I'm going to draw in the parts that you can't see. So in this one, you actually have a couple options for what you want to consider the bases, because I can say that these two faces are the bases of this prism, right? Because they're congruent and they are in parallel planes, so those are definitely bases. I can also consider this and this bases, but I think what most people prefer is to consider that and this top piece, right, the bases. So just like in 2D, you have a lot of options, right? In 2D, if you had a triangle like this, you might consider this to be the base and that to be the height, most likely, right? But you could also, let me draw this a little differently, right? So base and height, but you could also consider, let's say, this guy over here to be the base, right? And maybe that's the height. So just like in 2D, you have options when you have a rectangular prism, at least like this. And for a triangular prism, right, these have to be your bases. Those are congruent faces in parallel planes. Even if, let's say, these two quadrilaterals were congruent, right, those cannot be the bases of this prism because they intersect, of course. And for a cube, all right, again, lots of options for what you want to consider the basis of that prism. So once you've picked out a base, let's say I made this the base of my prism. Well, isn't this solid just made up of a lot of these thin slices? If I keep adding these thin slices, for example, right? If I add, think of them as like paper thin. If I add like a whole lot of them, right, I would form this solid. So 3D is kind of just like an extrusion or a pulling out of 2D. So if I wanted to find the volume of this rectangular prism, well, I think you all know volume we can find as length times width times height, right? It's three-dimensional, right? Volume is 3D. That's why we multiplied 3 dimensions together. That's why when we find area, we do length times width or base times height. We're multiplying two things. Or even for a circle, it's pi r squared. We're really doing r times r, right? We're multiplying two lengths, right? Two one-dimensional units together. Well, in 3D, we're multiplying 3 units together, right? Length, width, and height. And they are all units, right? They're all inches, 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 centimeters, 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 which is why volume is units cubed. So volume is really just the number of cubic units, the number of 1 by 1 by 1 cubes you can fit in the figure. So let's pretend the area of this face was 4. So we can have 4 squares there, right? So what would the volume of this guy be? Well, really that depends on how long this width is, right? So if it's 6, obviously the volume is 4 times 6, it's 24. And that's because, well, if I start pulling it out, I'm going to get these 3D cubes. And let's say this was 4 units. this way. And this was 1 unit this way, right? So in the red, what I highlighted, right? That's 2D area. That's 4 units squared. So the area I have right now is 4 units squared. If I say that's 1 more unit, don't I have 4 cubes now, 4 cubic units? So how far or how many cubic units I can fit all depends on that width. So it's really just length times width times height. But think about how I found the volume here. Then I use the area of this base, right? And then I multiplied it by the third dimension. So I know third dimension is W here, but typically we're going to be calling that H, or the height. So the volume of this prism, we can say, is the area of that base, right? We're going to use a capital B times the height. So again, we have lots of options for the base. So I made that front-looking face the base here, but I could have also made that, of course, the base, right? And the volume would be the same. The volume would be the area of this base down here times how much it's pulled. So in this case, I'm not pulling it that way, right? In this case, I'm pulling it up. I'm stacking, you can think, lots of flat sheets of paper on top of each other. And really the volume is just based on this area and how high do we need to stack it up to fill in the solid. And that's going to be the volume of the solid. So it's the area of this base times this height, right? I'm pulling it up. So volume is base times height. And base, it's a capital B, it's the area of the base times the height. And if you think about the units, right? Volume, again, that's units cubed, or cubic units. Capital B, that's an area, so that's going to be square units. So if we're doing square units times a length, like height, right? Height is just units. Square units times units is units cubed. Right, same thing for a triangular prism. In this case, we only have one base that we can consider, that one, and it's going to be the area of that base times the height. Same thing, that's the volume of that triangular prism. In fact, for any prism, that is going to be our formula, right? Because it doesn't matter what the base looks like, whatever that area is, right, times the height, that's going to be the volume. So even if the base looked like, I don't know, looked like this, if I wanted to find the volume of, I'm going to try my best here, of this figure, it would just be the area of, one sec to highlight, just be the area of this weird looking base times the height, right? So even though this is not a polygon anymore because I have rounded curves and smooth edges, right? It's still going to apply even though it's not a prism, right? It's still the area of that base, capital B, times the height. Right, but it's not a prism because it's not a polygon anymore on the bottom, but still volume is base times height. Same thing for a cube, right? For a cube, we know the volume is side times side times side, right? But if we look at that base, right, the area of that base is side times side, right? So times the height is side of it. So that is how we're going to find the volume of things like prisms. So let's move on to Cavalieri's principle now. And let's take a look at these two cylinders over here. And which cylinder do you think has the greater volume? So let's assume that these two bases are congruent, right? So assuming those two bases are congruent, and that height is 15 inches, which one is going to have the greater volume? So sometimes people say this one has a greater volume because they say, oh, that's slanted. So that's going to be longer therefore the volume has to be greater, but actually these two cylinders would have the same volume. And so again, think about the stacking, right? Think of this like a sheet of paper, and then I stacked a whole bunch of sheets of paper to make that volume. Or you can think of it like a loaf of bread, where the slices of bread are really, 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 really thin, right? And you stack it up to make the volume. So same thing here. I have that area, and let's say I cut this cylinder. I get something called a cross section. So let's say the cross-sectional area over here is that circle. Well, wouldn't this have the same cross-sectional area? Right? I'm stacking up the same areas. If I cut this cylinder over here, I get that cross-sectional area. And that's going to correspond with this cross-sectional area. So I'm stacking up all of the same areas in both of these cylinders. Right? It's kind of like I'm just tilting one of the cylinders, but the things I'm adding up, they're all the same. So the volumes are going to be the same, right? Essentially, think of this as if this were like a flexible rubber tube or something. And I kind of just pushed it over, right? Just because I changed the shape of it a little bit, I just tilted it, doesn't mean I changed the volume of it. The volume is still going to be the same in both solids. So that's something called Cavalieri's principle. So here are some objects in real life that might make it simpler to visualize, right? If we have a stack of coins, right, you can put your finger here and push the coins over a little bit, and it might end up looking like this. But those volumes, of course, are the same. You have the same number of coins, right? The volume of each coin is consistent. Same thing with a stack of CDs, right? This is kind of exactly like our example over here, where we just push the stack of CDs over a little bit. Volumes are going to be the same. So Cavalieri's principle actually applies not only when the cross-sections are exactly the same, but when the cross-sections have the same area, right? So the area of that cross-section here is 30 units squared. And if you find the area of this cross-section for that circle, that's also going to be 30 units squared. So if we're stacking up the same areas to the same height, right, the solids are going to have the same volume. So let's write this down. That is Cavalieri's principle. Cavalieri's principle states that if two or more figures have the same cross-sectional area at every level. Right? So at every level means this level, areas are the same. That level, areas are the same. Right? That level, areas are the same. So as us have the same area at every level and the same height, then the figures must have the same area. Actually, instead of figures, I'm going to say solids. Then the solids must have the same, I think I said area before. Of course, I mean volume, right? They have to have the same volume. So I'm also going to change that figures to solid. All right, let me read this to see if it sounds right. Cavalieri's principle states that if two or more solids have the same cross-sectional area at every level and the same height, then the solids must have the same volume. Yeah, perfect. All right, hopefully that makes sense. All right, every cross-section, if every cross-sectional area is the same, they're all congruent, they're both the same height, well then the volumes must be the same. And that really helps us with these prisms, because these prisms, they don't have to be going straight up at right angles. These prisms could be tilted, and we would still know how to find the area, right? I keep saying area. And we still know how to find the volume, right? The volume would still just be the area of the base times the height, right? Even if it was tilted, we could still find the height of the prism and get the volume. So if you know how to find the volume of the cylinder, you know how to find the volume of the tilted cylinder. It's actually exactly the same, right? Volume for a cylinder, it's still going to be area of the base times the height. So let's say you were given this tilted cylinder. We're missing information here, but let's say the radius was, let's make it up, let's say it's 4, right? If I wanted to find the volume of this guy now, the volume would be area of the base. So the base here is a circle, that's going to be pi r squared. So pi r squared, 4 squared, that's 16. So I'm just going to write 16 pi times the height. And well, the height is 15, so the volume is just 16 times 15, what is that? 225 plus another 15, 240. It's just 240 pi. And don't forget we're talking about volume, so units cubed. I'm just double checking the math. Yep, all right, looks good. So it would be the same exact way that you find the volume of that. So let's take a look at 2 practical examples, and that's going to be it for today. All right, so a pretty quick lesson. If you want, you can try these first on your own. All right, so let's check. If the total surface area of a cube is 450 square meters, find the volume of simplest radical form. All right, so hopefully you all know your vocabulary and you know what surface area is. All right, surface area is the sum of the area of all the faces. You can also think of it as the lateral area plus the area of the 2 bases. So in this case, it's a cube, so all 6 surfaces are going to have the same area. And so we can say area of a face is going to equal 450 divided by 6, right? 6 sides to the cube. And what is that equal to? I think 75. So area of any of these faces is 75 units squared, which means, well, that's 75. And isn't that a base of my cube? Right, that's 75. So all I need to do now is multiply by this height or width or extrusion, if you will. So we're pulling it out by a length of, what was it? Oh yeah, so sorry, I guess I should find one of the side lengths. So if the area is 75 units squared, well, let me just call it x, right? If those are x, can I say x squared, x times x equals 75. So x is the square root of 75. So all my dimensions are root 75. So the volume is area of the base. We said the area of the base is 75. If you want to do side times side times side, that's also fine. So it's going to be equal to 75 times the height. We're at 75. Let's get this in simplest radical form. So let's change that to what's 75 equal to? 25 and 3. 75 times 5, what is that? 375 root 3. And don't forget units cubed. Or you can write cubic units. Boom. All right. All right, next. An oblique hexagonal prism has a base area of 68 square meters. All right, this word oblique just means slanted, right? It means it's not right. Usually, most of the prisms we look at are right prisms. So This, for example, is a right prism because it goes straight up 90 degrees, or at least that's what I assumed when I looked at it, right? I really shouldn't make any assumptions, but let's say this is a right prism, right? This is also a triangular right prism because this goes straight up. That is 90 degrees. This here is 90 degrees, right? This here is 90 degrees. It's all 90 degrees. So those are called right prisms. When they do not go straight up 90 degrees, we call that an oblique prism, right? But still a prism because we still got two congruent base faces, right? Two congruent bases that are connected by parallel edges, and those bases, of course, are in parallel planes. So an oblique hexagonal prism has a base area of 68. Ah, we're already halfway done. You know, the volume of any prism is area of the base times the height. They already just gave us the area of the base. They told us it was 68 square meters, right? So that was very, very nice of them, right? They could have gave us like one of these lengths and told us it was a regular hexagon or something and asked us to find the base, which would be a lot more work, but they just gave this to us, 68 square meters. So all we have to do now is find the height. So the lateral slant side length is 10 radical 2 meters. All right, you gotta be careful. That is not the height of the prism, right? That's the slant height. So the height that we want to multiply by is going to be this height, right? Just think about when we looked at the cylinder, right? This was not the height of the cylinder. The height of the cylinder is this, right? A vertical height. So we need to find that vertical height. The lateral side makes an angle of 45 degrees with the horizontal plane containing the base, as shown. What is the volume? So the height, well, I got a right triangle here. Even better than a right triangle, I got a 45, 45, 90 right triangle. Because they told us that was 45 degrees. And the slant height was 10 radical 2. So hopefully remember your 45, 45, 90 right triangles. If you do not, it's x, x, x radical 2, right? Which makes those side lengths 10 each. And so the volume is 680, trying to think of the units, meters cubed. Bam. And that is all. So that's going to be it for today's lesson. Just make sure you understand Cavalieri's principle, and very simple, that the volume of any base, sorry, not any base, the volume of any prism is the area of the base times its height. All right, so that is going to be it. I hope you guys are staying safe. Take care, and I'll see you guys soon.